So today we're looking at the fundamental theorem of calculus, and here we have what are known as definite integrals, okay? Now we've talked about the fact that the integral gives us the area under the curve. In fact, that first exercise that you guys were doing, you were introduced to that concept of on an interval, what is the area under this curve, okay? And that was great as long as you had rectangles and trapezoids and triangles or something else that you actually could find the shape of geometrically, find the area of. However, integration and these antiderivatives that we've been learning are really the way that we are going to be able to find the area under any curve, even if it isn't a recognizable geometric shape. Okay, and that's where we have this definite integral. Okay, so let's read this fundamental theorem of calculus. If capital F of x is the antiderivative of f of x, where f of x is continuous on an interval from a to b, then the definite integral of f of x on this integral is, and this is how you would read this, the integral from a to b of f of x dx equals capital F of b minus capital F of a. All right? Okay. So, let's talk about what in the world this means. Now, to do this, let's draw a quick sketch, okay? Let's say that we have some kind of a function like this, okay? Not a geometrical shape that we recognize or can find the area under. But then we have this interval from A to B. First of all, one thing that's important is that our function has to be continuous. If there was a hole, or if there was some kind of an asymptote, or if this were a piecewise function and a discontinuity that way, we could not get the definite integral on A to B, okay? But here we can. The area that we are looking for is this area right here, okay? It's underneath the function and above the x-axis, or I should say between the function and the x-axis, and also between A and B, okay? So you can even draw these lines here if you like to hem that in, okay? Now, so what is this whole capital F of B minus capital F of A thing? Well, let's look at this. Capital F of B is the antiderivative evaluated at B. So all those antiderivatives we've been finding, you would plug in this upper limit or upper bound of the definite integral, okay? Now, what that will give you is the area under the curve from B all the way to the y-axis. Okay? Now, clearly, that's more of the area than we wanted, right?
But that's why it's F of A, you just subtract whatever.
Exactly. That's why we do f of a. Capital F of a is going to give us the area from A over to the y-axis. And guess what? That's the little bit of extra we don't want, which is why we're subtracting. Mm-hmm. Okay? Does that make sense?
Yes.
Yeah.
Okay? So, capital F of B gives us from here all the way over. Capital F of A gives us the extra bit, and we subtract it, and that gives us just the area between A and B. Okay? That's what we're doing here with the fundamental theorem of calculus. Now, there are a lot of variations. Okay? There's a lot of variations to this. For example, let me give you one other sketch. Let's say that we had a function that was on, like this again. And let's say A was over here and B was over here. Okay? Now we're still getting the area between A and B. Okay? But notice here, well, B again would go from here, capital F of B would be from here to here. Because capital F of A would be going the opposite direction, in other words, it has to go to the right to get to the y-axis, that's going to be a negative value. So when we subtract the negative value, we're actually adding it. So that's how it ends up giving us the total area. Okay? So we end up doing a minus a negative. And it gives us a minus a negative area. And I know that seems kind of weird, but that's what's happening. Okay? Now, there is one distinction that that I want to make right here at the beginning, and that is when we're doing applications of these integrals. This is a negative area because instead of going from the y-axis to the right, like we did to get to B, we're actually going from the y-axis to the left, and anytime you're integrating going to the left, it makes it negative. Okay, so let's look at this. The area under a curve. What exactly do we mean? This word under is a little bit deceiving, okay? Because clearly, if our function went below the x-axis, under that would be infinity, okay? So when we say the area under the curve, we're talking about the area between the function and the x-axis, okay? It's between the function and the x-axis. Anything that is below the x-axis would be a negative. Okay? Just like what we just saw, anything to the left, if we're going from the y-axis to the left, it's negative. Okay? Anything below the x-axis is negative as well. Okay, so there's two ways we can get negative areas with integrals. Okay? There's two ways to get negative areas. One is to have something below the x-axis. The other is if I'm integrating, instead of going from A to B, if I went from B to A, if I go backwards, like we just saw in the previous example when we did f of A, it gives us a negative value as well. Okay?
Wait, so you...
Alright, so I want to use a little bit of this in order to, with some ones that we can do geometrically, just so we get used to the notation. Okay? So first of all, A here. We have the integral from 0 to 4 of f of x dx. And over here I have f of x. So that's going to give me this, right? I've got a semicircle. So what's the area of that semicircle? 1/2 pi r squared. What's the radius?
4, so it's,
No.
2.
Radius is 2.
So 1/2 pi r squared would be pi over 2.
1/2 pi times 2 squared
4, so 2 pi.
is 2 pi. Okay? So that integral is 2 pi. Okay? Okay? Now we have part B. Part B is the integral from 6 to 4. Or I'm sorry, 4 to 6. So that's this right here. Okay?
That's just 4.
What does that integral equal?
4. -4.
Negative 4. It's below the x-axis, right?
Right.
Okay?
Why is it negative 4?
It's below the x-axis.
Or is the
Because it's 2 times 2, because each sideline is just a square.
Write down the blue.
body?
Okay? So that's negative 4. This was 2 pi. And now part C. Part C.
It's just 2 long, so it's 2 pi 2, no, 2 pi 1 squared.
Okay? It's half of, because it's a semicircle, pi times, what's the radius? 1. Okay, so this is pi over 2. And it's above the x-axis, so that is the area. Yeah, it's positive. Okay?
Not what you were asking.
Now, question for D. Okay? D.
Answer for you.
If we mix all those colors, we'll probably get some kind of brown looking thing, so we'll use that. Okay? What would the integral from 0 to 8 equal?
The sum of that. The sum of those 3.
Okay?
I'm wrong.
All of them multiplied together.
Well, no, you're on the right track, okay? At least for the idea of the problem. We have 2 pi minus 4 plus a half a pi. So that would equal 2.5 pi minus 4. Now, that's kind of what we're supposed to see. Technically speaking, though, someone tell me why I cannot actually do the integral from 0 to 8.
There's a hole. No.
There's what?
Is it because of the hole at 0?
Well, no, that's just indicating the origin. Why can't I technically do the integral?
Because it's not continuous from 4 to 6.
It's not continuous.
Yeah, it's not.
Right?
It's not real.
I have these jumps right here at 4 and at 6. Okay? So, actually, we can't do this because f of x is not continuous on the interval from 0 to 8. Okay?
Why is it continuous?
Because I got a jump there at 4 and at 6. I had that semicircle and then the horizontal line down at -2 and then another semicircle, and they weren't actually
I have
connected.
a question. So you can do the integral of 4 to 6, that little box, you can do that, and that's perfectly fine alone?
Yes, because the function is continuous from 4 to 6. It can be an open interval.
Because it's just a line.
Actually, and technically speaking, what I ought to be doing here, I ought to have parentheses instead of brackets, because it's okay if there's a discontinuity at the end, at an end point, but it can't be anywhere in the middle of the interval.
I just realized those are dotted lines.
Okay? Yeah, those are little dotted lines. Otherwise, it wouldn't be a function at all.
Yeah,
Cause,
that's what I
Yeah.
thought initially, because I thought it was going to say it's not a function, because it's just a box.
yeah. Okay, so here are several rules for definite integrals, or properties of definite integrals. Okay? Let's take a look at these really quickly, and actually a lot of these are pretty self-explanatory if you think about it. Okay? The integral over an interval of one value. Okay? Let's flash back to geometry.
Oh boy.
Okay?
Mr. Sackdays.
When we had some kind of a function, if this is a, the interval from a to a is a line segment. Okay? You guys know that a line segment has no area.
Yes, I did.
Okay? So the integral from a to a would just be the area of this little line segment going straight up from a to the function, which has no area. Okay?
Okay.
Alright.
Line segment no area. Okay? Here's another one. Integral over an interval from right to left. Notice we had our intervals were going from A to B. Okay? And here we're understanding that A is less than B. Okay? So if we go from right to left, from B to A, that's going to give us the negative or the opposite of the integral from A to B. If you think about it, in terms of our fundamental theorem of calculus, that makes sense. This would be capital F of A minus capital F of B, right? This would be capital F of B minus capital F of A, which is the opposite. So negative 1 times that. So those would be equal then. Okay?
So B one.
Square.
Or square, yeah.
Okay? Then we have the one I illustrated there when we had to find total area. If I have some value in the middle of an interval, I can find the integral from A to B if I take the integral, or I'm sorry, from A to C, if I take the integral from A to B and then add the integral from B to C. Okay? Again, a quick sketch. Here's A, there's C, and there's B. It just makes sense if I take the area from A to B and I add to it the area from B to C. Now I've got the area all the way from A to C. Okay?
But, hold on.
So the integral from A to B plus the integral from B to C equals the integral from A to C.
What do orange and blue mean?
I don't know. Florida.
No. I can't write Florida.
University of Florida.
Gators.
Ugly. I don't know. Alright, integral of a sum or a difference. Integral of a sum or a difference. This is one thing that's going to be really, really useful and allows us to do lots more different functions. Okay?
I guess you could say it
But
moves.
if I'm taking the integral of two functions, added or subtracted, I can simply take the integral of the one function and the integral of the other function and add or subtract those values. Okay? So if I had something like the function x squared plus sine of x, I could take the integral of just the x squared and the integral of just the sine of x and then add those two things together at the end. We did this already with our indefinite integrals. Okay?
There's no difference?
No difference. Okay? The integral of a constant. Okay? The integral of a constant. The only reason why we look at this one here is, again, if I look at a sketch of this, if we have a constant function like this, and I go from A to B, that area is going to be what? What shape do I have?
Rectangle.
A rectangle. Okay? So, if this constant is going through y equals c, then that means the rectangle has a height of c and the base is b minus a. Okay? So you don't even have to really go through the whole process of doing the antiderivative and the fundamental theorem. You can just write down the area of that rectangle. C times b minus a. Okay?
Gotcha.
And then finally, the constant multiple. We saw this with our antiderivatives. It still applies. If you have something like 5 sine of x, that you're taking the integral of, you can pull the 5 out, do the integral of sine, and then multiply your final answer by the 5. That's really helpful, especially if you have some weird values in there. For example, if I were doing, let's say, the integral from pi over 6 to pi over 3 of, let's say, a pi over root 3 sine of x dx. Well, that pi over root 3 is going to be kind of annoying to work with as we're doing this whole integration process. Okay? So what we are able to do with this property is I can pull that pi over root 3 out and just do the integral of the sine of x from pi over 6 to pi over 3. Okay? And then you're able to do 90% of the work here with just leaving this pi over root 3 on the outside. Okay? And this one I actually want to do because I want to show you the notation that we will use as we're doing this. Okay, so let's actually do this whole example. If I have the antiderivative of sine, what does that equal? Negative cosine. So I'm doing negative cosine x. Now, I don't need the plus c. Okay? Because if I did the f of b minus f of a, I would have a plus c and then a minus c, and they'll cancel each other out. Right?
Yeah.
So, I don't need the plus c. But I need to evaluate this from pi over 6 to pi over 3. Now, what is the negative cosine of pi over 3?
Pi over 3, that'd be negative 1/2? Question mark?
Yes. Okay, question mark. Pi over root 3 times, that's going to be negative 1/2. And then minus a negative, what's cosine of pi over 6?
Radical 3 over 2.
Radical 3 over 2. You
Yeah,
all
man.
know because you know your unit circle.
Yes, we do.
Okay.
Definitely.
So, now I'll multiply by that pi over root 3. Okay? So I have negative pi over 2 root 3 plus a pi over 2.
Really like that?
Sure. Okay?
Cool.
But notice I didn't have to mess with that while I was doing the whole integral and everything. I pull out the constant multiple, and then I can multiply it by it at the end. Okay? All right. Now, this is a little tutorial on how to use your calculator. Okay? You can use this to check your answers on problems where you're allowed to use the calculator, or there will be ones that we simply don't know the rules for. Okay?
You don't know.
So let's look at how we would do this on the calculator. Okay? So I'm going to insert a new video here.